Alright, my name's Andrew Coble, and this is my Project 1 presentation for CE 570. Studied through the MATLAB examples already defined, I decided to code an upright cone. This is where the base of the cone is at the height h and the tip of the cone is at the origin. I started out by defining my constants such as r representing the radius of the cone, h representing the height, and t representing the revolution of my cone. I then provided the number of divisions each grid will be broken up into. Here is where I introduce the radial parameter d, which defines how the radius extends from the bottom of the cone to the top. So initially I had to define the radius as r, but later I changed it to d so it could scale the cone's geometry directly. Next I define the body's parameters, which is the radius divided by the height multiplied by z, d, and cosine of t. Then radius divided by height multiplied by z, d, and sine of t, and then z, which are x1, x2, and x3 dimensions respectively. After that, I defined the surfaces and curves of my cone, which was quite unique compared to the existing examples. I made the difficult choice to hard code 1 to some of my boundary values to make it simpler for the project and keep it similar to the current format as possible. Next, I defined a curved surface along my cone. This line wraps around my cone and makes one revolution around the exterior. My surface spans roughly pi over 3, which is a sixth of a revolution, and begins at the base of the cone at the top and stretches along the exterior to the base vertex of the cone at the origin. Here is an image of my upright cone output for my code. First off, you can see the defined curve that is in red and completes one revolution around the cone. You can also see that the surface plotted in blue that covers about pi over 3 revolution around the exterior of the cone and stretches down the side of the cone to the origin. In this slide, I will go over the outputs that MATLAB gave me and how I was able to converge both the length of the curve and the surface area. The image on the top left is the curve with 10 segments at a length value of 7.426. Then the next image is at 100 segments, 500, 1,000, and 2,000 respectively, when it finally converges at a value of 7.5514 at 2,000 segments. The bottom image is of the surface area with 10 segments in both directions with an area of 3.9629. I continued the same process to get the surface area to converge by adding more segments like 100, 1,000, 2,000, but by even going up to 10,000, but didn't get the same response for the area to converge completely. But I did get it pretty close at around 2,000 segments with a surface area value of 3.6074. I began my hand calculations by parameterizing the body by hand, where the 2/3 constant at the front of the parameters represented radius over height. The three parameters are d, which is the scaled radial coordinate that runs from 0 to 1 and helps model the radius from the origin to the top of the base of the cone rather than representing it as r over h times z. The second parameter is t, which represents the angle around the cone, which runs from 0 to 2 pi. The third parameter is z, which represents the vertical height of the cone and runs from 0 to 3, which is also h. I was able to verify the length of my line by deriving the equation by hand. I took the derivative of each of the equations using a derivative calculator and then taken the square root and integrated from 0 to 1. I then plugged the constants into the equation and integrated to get the length of 7.5514, which matches the length I got from my MATLAB code. Finally, I was able to verify the area of my surface by deriving the equation by hand again. I found the derivatives with respect to t and s, which were the two parameters that run from 0 to the number of segments, which in this case was 10. I then took the cross product of these values and normalized them. After that, I integrated with respect to s and then t. Since my surface only had a revolution of pi over 3, I had that as my upper bound. Following integration, I plugged in the required constants and came up with a surface area of 3.7757, which is slightly different than the MATLAB surface area of 3.6074. I attribute this to the cone surface being curved and MATLAB having a hard time getting the exact area with an approximation calculation. This calculation gets close enough to the exact surface area.